The history of geology is concerned with the development of the natural science of geology. Geology is the scientific study of the origin, history, and structure of the Earth. Antiquity. Some of the first geological thoughts were about the origin of the Earth. Ancient Greece developed some primary geological concepts concerning the origin of the Earth. Additionally, in the 4th century BC, Aristotle made critical observations of the slow rate of geological change. He observed the composition of the land and formulated a theory where the Earth changes at a slow rate and that these changes cannot be observed during one person's lifetime. Aristotle developed one of the first evidentially based concepts connected to the geological realm regarding the rate at which the Earth physically changes. However, it was his successor at the Lyceum, the philosopher Theophrastus, who made the greatest progress in antiquity in his work on stones. He described many minerals and ores both from a local mine such as those at Laurium near Athens, and further afield. He also quite naturally discussed types of marble and building materials like limestones, and attempted a primitive classification of the properties of minerals by the properties such as hardness. Much later in the Roman period, Pliny the Elder produced a very extensive discussion of many more minerals and metals than widely used for practical ends. He was among the first to correctly identify the origin of amber as a fossilized resin from trees by the observation of insects trapped within some pieces. He also laid the basis of crystallography by recognizing the octahedral habit of diamond. Middle Ages. Abu al-Rayhan al-Biruni was one of the earliest Muslim geologists, whose works included the earliest writings on the geology of India, hypothesizing that the Indian subcontinent was once a sea. Ibn Sina, a Persian polymath, made significant contributions to geology and the natural sciences along with other natural philosophers such as Iqnai Safa and many others. Ibn Sina wrote an encyclopedic work entitled Kitab al-Shifa, in which Part 2, Section 5, contains his commentary on Aristotle's mineralogy and meteorology in 6 chapters. Formation of mountains. The advantages of mountains in the formation of clouds, sources of water, origin of earthquakes, formation of minerals, the diversity of Earth's terrain. In medieval China, one of the most intriguing naturalists was Shen Kuo, a polymath personality who dabbled in many fields of study in his age. In terms of geology, Shen Kuo is one of the first naturalists to have formulated a theory of geomorphology. This was based on his observations of sedimentary uplift, soil erosion, deposition of silt, and marine fossils found in the Taihang Mountains, located hundreds of miles from the Pacific Ocean. He also formulated a theory of gradual climate change, after his observation of ancient petrified bamboos found in a preserved state underground near Yanzhou, in the dry northern climate of Shaanxi Province. He formulated a hypothesis for the process of land formation, based on his observation of fossil shells in a geological stratum in a mountain hundreds of miles from the ocean. He inferred that the land was formed by erosion of the mountains and by deposition of silt. 17th century. It was not until the 17th century that geology made great strides in its development. At this time, geology became its own entity in the world of natural science. It was discovered by the Christian world that different translations of the Bible contained different versions of the biblical text. The one entity that remained consistent through all of the interpretations was that the deluge had formed the world's geology and geography. To prove the Bible's authenticity, individuals felt the need to demonstrate with scientific evidence that the Great Flood had in fact occurred. With this enhanced desire for data came an increase in observations of the Earth's composition, which in turn led to the discovery of fossils. Although theories that resulted from the heightened interest in the Earth's composition were often manipulated to support the concept of the deluge. A genuine outcome was a greater interest in the makeup of the Earth. Due to the strength of Christian beliefs during the 17th century, the theory of the origin of the Earth that was most widely accepted was a new theory of the Earth published in 1696 by William Whiston. Whiston used Christian reasoning to prove that the Great Flood had occurred and that the flood had formed the rock strata of the Earth. During the 17th century, the heated debate between religion and science over the Earth's origin further propelled interest in the Earth and brought about more systematic identification techniques of the Earth's strata. The Earth's strata can be defined as horizontal layers of rock having approximately the same composition throughout. An important pioneer in the science was Nicholas Steno. Steno was trained in the classical texts on science. However, by 1659 he seriously questioned accepted knowledge of the natural world. Importantly, he questioned the idea that fossils grew in the ground, as well as common explanations of rock formation. His investigations and his subsequent conclusions on these topics have led scholars to consider him one of the founders of modern stratigraphy and geology. 18th century. For this increased interest in the nature of the Earth and its origin, came a heightened attention to minerals and other components of the Earth's crust. Moreover, the increasing economic importance of mining in Europe during the mid to late 18th century made the possession of accurate knowledge about ores and their natural distribution vital. Scholars began to study the makeup of the Earth in a systematic manner, with detailed comparisons and descriptions not only of the land itself, but of the semi-precious metals it contained, which had great commercial value. For example, in 1774 Abraham Gottlob Werner published the book Von den Östlichen Kennzeichen der Fossilien, which brought him widespread recognition because he presented a detailed system for identifying specific minerals based on external characteristics. The more efficiently productive land for mining could be identified and the semi-precious metals could be found, the more money could be made. This drive for economic gain propelled geology into the limelight and made it a popular subject to pursue. With an increased number of people studying it, came more detailed observations and more information about the Earth. Also during the 18th century, aspects of the history of the Earth, namely the divergences between the accepted religious concept and factual evidence, once again became a popular topic for discussion in society. In 1749 the French naturalist Georges-Louis Leclerc, Comte de Buffon, published his Histoire naturelle, in which he attacked the popular biblical accounts given by Whiston and other ecclesiastical theorists of the history of Earth. From experimentation with cooling globes, he found that the age of the Earth was not only 4,000 to 5,500 years as inferred from the Bible, but rather 75,000 years. Another individual who described the history of the Earth with reference to neither God nor the Bible was the philosopher Immanuel Kant, who published his Universal Natural History and Theory of the Heavens in 1755. For the works of these respected men, as well as others, it became acceptable by the mid-18th century to question the age of the Earth. This questioning represented a turning point in the study of the Earth. It was now possible to study the history of the Earth from a scientific perspective without religious preconceptions, with the application of scientific methods to the investigation of the Earth's history. The study of geology could become a distinct field of science. To begin with, the terminology and definition of what constituted geological study had to be worked out. The term geology was first used technically in publications by two Genevan naturalists, Jean-André de Luc and Horace Benedict de Saussure, though geology was not well received as a term until it was taken up in the very influential compendium, the Encyclopédie, published beginning in in 1751 by Denis Diderot. Once the term was established to denote the study of the Earth and its history, geology slowly became more generally recognized as a distinct science that could be taught as a field of study at educational institutions. In 1741, the best-known institution in the field of natural history, the National Museum of Natural History in France, created the first teaching position designated specifically for geology. This was an important step in further promoting knowledge of geology as a science and in recognizing the value of widely disseminating such knowledge. By the 1770s, chemistry was starting to play a pivotal role in the theoretical foundation of geology, and two opposite theories with committed followers emerged. These contrasting theories offered differing explanations of how the rock layers of the Earth's surface had formed. One suggested that a liquid inundation, perhaps like the biblical deluge, had created all geological strata. The theory extended chemical theories that had been developing since the 17th century and was promoted by Scotland's John Walker, Sweden's Johann Gottschalk Wallerius, and Germany's Abraham Werner. Of these names, Werner's views became internationally influential around 1800. He argued that the Earth's layers, including basalt and granite, had formed as a precipitate from an ocean that covered the entire Earth. Werner's system was influential, and those who accepted his theory were known as Diluvianists and Neptunists. The Neptunist thesis was the most popular during the late 18th century, especially for those who were chemically trained. However, another thesis slowly gained currency from the 1780s forward. Instead of water, some mid-18th century naturalists such as Buffon had suggested that strata had been formed through heat. The thesis was modified and expanded by the Scottish naturalist James Hutton during the 1780s. He argued against the theory of Neptunism, proposing instead the theory of based on heat. Those who followed this thesis during the early 19th century referred to this view as Plutonism, the formation of the Earth through the gradual solidification of a molten mass at a slow rate by the same processes that had occurred throughout history and continued in the present day. This led him to the conclusion that the Earth was immeasurably old and could not possibly be explained within the limits of the chronology inferred. For the Bible, Plutonists believed that volcanic processes were the chief agent in rock formation, not water from a great flood. 19th century. In the early 19th century, the mining industry and industrial revolution stimulated the rapid development of the stratigraphic column, the sequence of rock formations arranged according to their order of formation in time. Quote, in England, the mining surveyor William Smith, starting in the 1790s, found empirically that fossils were a highly effective means of distinguishing between otherwise similar formations of the landscape as he traveled the country working on the canal system and produced the first geological map of Britain. At about the same time, the French comparative anatomist Georges Cuvier, assisted by his colleague Alexandre Brongniart at the École des Mines de Paris, realized that the relative ages of fossils could be determined from a geological standpoint, in terms of what layer of rock the fossils are located and a distance. These layers of rock are from the surface of the Earth. Through the synthesis of the findings, Brongniart and Cuvier realized that different strata could be identified by fossil contents, and thus each stratum could be assigned to a unique position in a sequence. After the publication of Cuvier and Brongniart's book, Description géologique des environs de Paris, in 1811, which outlined the concept, stratigraphy became very popular amongst geologists. Many hoped to apply this concept to all the rocks of the Earth. During this century, various geologists further refined and completed the stratigraphic column. For instance, in 1833, 1923, while Adam Sedgwick was mapping rocks that he had established were from the Cambrian period. Charles Lyell was elsewhere suggesting a subdivision of the Tertiary period, whilst Roderick Murchison, mapping into Wales from a different direction, was assigning the upper parts of Sedgwick's Cambrian to the lower parts of his own Silurian period. The stratigraphic column was significant because it applied a method to assign a relative age of these rocks by slotting them into different positions in the stratigraphical sequence. This created a global approach to dating the age of the Earth and allowed for further correlations to be drawn from similarities found in the makeup of the Earth's crust in various countries. In early 19th century Britain, catastrophism was adapted with the aim of reconciling geological science with religious traditions of the biblical Great Flood. In the early 1820s, English geologists including William Buckland and Adam Sedgwick interpreted diluvial deposits as the outcome of Noah's flood, but by the end of the decade they revised their opinions in favor of local inundations. Charles Lyell challenged catastrophism with the publication in 1830 of the first volume of his book Principles of Geology, which presented a variety of geological evidence from England, France, Italy, and Spain to prove Hutton's ideas of gradualism correct. He argued that most geological change had been very gradual in human history. Lyell provided evidence for uniformitarianism, a geological doctrine that processes occur at the same rates in the present as they did in the past, and account for all of the Earth's geological features. Lyell's works were popular and widely read. The concept of uniformitarianism had taken a strong hold in geological society. During the same time that the stratigraphic column was being completed, imperialism drove several countries in the early to mid-19th century to explore distant lands to expand their empires. This gave naturalists the opportunity to collect data on these voyages. In 1831, Captain Robert Fitzroy, given charge of the coastal survey expedition of HMS Beagle, sought a suitable naturalist to examine the land and give geological advice. This fell to Charles Darwin, who had just completed his BA degree and had accompanied Sedgwick on a 2-week Welsh mapping expedition after taking his spring course on geology. Fitzroy gave Darwin Lyell's Principles of Geology, and Darwin became Lyell's first disciple, inventively theorizing on uniformitarian principles about the geological processes he saw, and challenging some of Lyell's ideas. He speculated about the Earth expanding to explain uplift, then on the basis of the idea that ocean areas sank as land was uplifted, theorized that coral atolls grew from fringing coral reefs round sinking volcanic islands. This idea was confirmed when the Beagle surveyed the Cocos Islands, and in 1842 he published his theory on the structure and distribution of coral reefs. Darwin's discovery of giant fossils helped to establish his reputation as a geologist, and his theorizing about the causes of their extinction led to his theory of evolution by natural selection, published in On the Origin of Species. In 1859, economic motivations for the practical use of geological data caused governments to support geological research. During the 19th century, the governments of several countries, including Canada, Australia, Great Britain, and the United States, funded geological surveying that would produce geological maps of vast areas of the countries. Geological surveying provides the location of useful minerals, and such information could be used to benefit the country's mining industry. With the government funding of geological research, more individuals could study geology with better technology and techniques, leading to the expansion of the field of geology. In the 19th century, scientific realms established the age of the Earth in terms of millions of years. By the early 20th century, the Earth's estimated age was 2 billion years. Radiometric dating determined the age of minerals and rocks, which provided necessary data to help determine the Earth's age. With this new discovery based on verifiable scientific data and the possible age of the Earth extending billions of years, the dates of the geological time scale could now be refined. Theories that did not comply with the scientific evidence that established the age of the Earth could no longer be accepted. 20th century. The determined age of the Earth as 2 billion years opened doors for theories of continental movement during this vast amount of time. In 1912, Alfred Wegener proposed the theory of continental drift. This theory suggests that the continents were joined together at a certain time in the past and formed a single landmass known as Pangaea. Thereafter they drifted like rafts over the ocean floor, finally reaching the present position. The shapes of continents and matching coastline geology between some continents indicated they were once attached together as Pangaea. Additionally, the theory of continental drift offered a possible explanation as to the formation of mountains. For this, different theories developed as to how mountains were built. Unfortunately, Wegener provided no convincing mechanism for this drift, and his ideas were not accepted during his lifetime. Research from 1947 found new evidence about the ocean floor, and in 1960 Bruce E. Heezen published the concept of mid-ocean ridges. Soon after this, Robert S. Dietz and Harry H. Hess proposed that the oceanic crust forms as the seafloor spreads apart along mid-ocean ridges in seafloor spreading. This led directly to the theory of plate tectonics that was well supported and accepted by almost all geologists by the end of the decade, and provided a mechanism explaining the apparent drift which Wegener had proposed. Geophysical evidence suggested lateral motion of continents and that oceanic crust is younger than continental crust. This geophysical evidence also spurred the hypothesis of paleomagnetism. The record of the orientation of the Earth's magnetic field recorded in magnetic minerals. British geophysicist S.K. Runcorn suggested the concept of paleomagnetism from his finding that the continents had moved relative to the Earth's magnetic poles. Modern geology, by applying sun stratigraphic principles to the distribution of craters on the Moon, it can be argued that almost overnight, Gene Shoemaker took the study of the Moon away from lunar astronomers and gave it to lunar geologists. In recent years, geology has continued its tradition as the study of the character and origin of the Earth, its surface features and internal structure. What changed in the later 20th century is the perspective of geological study. Geology was now studied using a more integrative approach, considering the Earth in a broader context encompassing the atmosphere, biosphere and hydrosphere. Satellites located in space that take wide-scope photographs of the Earth provide such a perspective. In 1972, the Landsat program, a series of satellites missions jointly managed by NASA and the U.S. Geological Survey, began supplying satellite images that can be geologically analyzed. These images can be used to map major geological units, recognize and correlate rock types for vast regions and track the movements of plate tectonics. A few applications of this data include the ability to produce geologically detailed maps, locate sources of natural energy and predict possible natural disasters caused by plate shifts.